lecture, we're going to look at nonlinear solver in PETC. It is called as SNES, and it stands for not the Super Nintendo Entertainment System, but it stands for Scalable Nonlinear Equation Solver. And we've had a look at the Newton iterations and all that in Python. But the fact is, when you're trying to solve differential equations, when you're trying to construct some residual, so the residual is defined as a times x minus b, and your target is to minimize this residual. So often this can be nonlinear. It can be polynomial, it can be transcendental, but what happens when it is nonlinear? So you need to solve for nonlinear algebraic equations, and that requires a scalable nonlinear solver. So the crux of solving something which we have already done, say for example you want to solve some f of x equal to 0, and this is a column vector which contains all the functions, and x is the vector x0, x1 and so on. I will see in an example what exactly this means. So if you have a multidimensional function, then f of x plus some step is equal to f of x plus the Jacobian evaluated at x times the step plus order s square. So this comes from a multidimensional Taylor series approximation. And this Jacobian, so what is this Jacobian? So Jacobian is defined as this particular matrix. So del f naught, del x naught, del f naught, del x1, so on, del f naught, del x n minus 1 if there are n number of elements in this, and similarly this becomes del f n minus 1, del x naught, all the way to del f n minus 1, del x n minus 1. So this is called as the Jacobian of this particular Taylor series. And so the point is, if we are near a root, right, so you are at some point in the parameter space, not the parameter space but the variable space x, and this is the solution. So if this were to be true, then f at x plus s would be equal to 0. This is that step s. So if you are having a good knowledge of what s is going to be, then after that particular step you would arrive at the solution. Therefore, add the solution f of x plus s is equal to 0. This implies 0 is equal to f of x plus the Jacobian of x times s. And if s is not the appropriate step, so if this is the solution, this is x, so if the Jacobian approximation at this point makes you go over here, then you hope that in the next iteration it will take you like this, then in the next iteration like this, and in the next iteration like this. And we have seen this in Python, how this looks, right? So the step, in order to evaluate what the step will be, we need to solve this particular linear equation. Right? We need to solve this equation. And once this is solved, we need to update what x is. So x will be simply updated by x plus s. So this is nothing but the update. So this is the step finding and this is the update, right? Let us consider a very simple example. So y is equal to 1 upon b exponential of bx, right? And x square plus y square equal to 1. So we need to solve these two equations simultaneously. And we know how the solution will look like. How? Because we've seen this already, that these two equations, the root will correspond to the intersection of these two equations. So let me draw an axis and let us draw the circle. So this is a circle at the origin. So it's something like this, right? It's a very poorly drawn circle, but you get the point. And the exponential will be something like this, right? So obviously it will intersect somewhere along minus x as well, some minus root, but it will intersect over here as well. So it is quite straightforward to graphically draw the root, but solving it algebraically is not possible, and therefore you have to resort to these kind of iterative methods. So what is the way we can achieve this in PETC? So let us start programming and I will explain the different terms as and when they arrive. So let us create a new file. Alright, so first things first, hash include petc.h, then int main argc, int argc star v. Let us save this. Let's call this nlin1.c. Alright, so first things first, we have to return petc finalize and we have to do an initialize. Apart from this, we must create the object that will help us in solving a nonlinear problem. In the case of the matrix solvers, we were using a KSP object. In this particular case, we'll be using a SNES object. So simply we declare SNES like we did for KSP. We will need two vectors. One vector will be X and one vector will be Y. R. So vec X comma R. So what is X? X is a vector which consists of x0 and x1, which is a stand-in for x and y, because we have a single array which will hold all the variables. So in that case, this particular equation can be written as x1 is equal to 1 upon b exponential of b x0. This will be x0 square minus x1 square is equal to 1. And so let us try to write it in this particular form, f of x equal to 0. So this particular form will be 1 upon b exponential of b x0 minus x1 and x0 square minus x1 square minus 1 is equal to 0. So this is that form that we spoke about. Okay, so let us continue. So we need, okay, so I did not explain what R is. R is the residual, okay, residual of these two equations. So it is obviously an array, okay. So this is required by the SNES solver because it provides us what residual has remained from solving this particular set of equations. Alright, so now that we have defined this, we will do a PETC initialize. So let me copy the code because PETC initialize looks the same. Mm, so instead of this, we will have solve a nonlinear equation. Alright, after this, we will create the vectors that we will require for our computation. So vec create PETC world ampersand x, so address of x, vec set sizes x comma PETC decide comma 2, so we want it to be of size 2. Then vec set from options x in case we pass command line arguments, and finally vec set. So this is a new function that we're using. Vec set is to declare that all the values in x will be set to 1. So this sets both the values to be 1. And why do we do this? Because we're going to start with an initial guess of 1 comma 1. If this is not required, we can do the entire sequence of setting a vector like we had done in the previous example. In creating the right hand side of the Poisson solver, we had created the vector in this fashion. We can do that. Well, you don't need to do all this, but you simply need to assign a value. But because we'll start with a guess of 1 comma 1, it's convenient to use this particular function quickly. Finally, let us duplicate x into r. So vec duplicate x into r. So the address of r is passed. So at this particular step, we have created the arrays. So this alright. So we've populated them with 1. Now we must create the SNES object. It follows the exact same sequence that we had followed for KSP. So first SNES create, let's see com world, we have to pass the address of SNES, then SNES set function SNES comma residual comma the function comma null. So let me show the command reference of set function. So what it does is it tells the SNES solver that whatever residual you have, you store it in R, and the function callback is funct. So we will create it. I have not yet created the function. We will create a function which will provide these two values. It's a simple function which will output a vector which will be comprised of these two things. So right, okay, well there's some okay, so it has the SNES context the residual storer, the function routine, and the user define parameters that you want to pass. But in this case, we'll not pass any user defined parameters. Okay, so that's it. It's as easy as that. So we've defined this. Once we've set the function, we can actually go ahead and create the function right now. Let us not wait for it. So let's see error code funct. So the funct will sort of take as an input SNES, the vector x, the vector f will be sort of returned, and the additional thing we need is the user context. So in this case, it will be void pointer to user context. All right. So the vector f is something which is going to hold the return value. So funct in this case is going to hold the return value. So we have const double b is equal to 2.0. So by a const double, we say that we are not even accidentally going to change the value of b. All right. All right. So apart from this, we need a pointer to the ax, because whatever, so ax is the auxiliary array for the vector x. Remember, for defining a vector in PETC, in case we want to print everything or run something in a loop, we need an auxiliary array. Like over here, we had a vec uexact, but we needed an auxiliary array a uexact. So that is the same thing. Alright, so it's a constant array, and the reason is we will not modify values of x. We simply want to modify values of f. That is why we will declare it as a constant double pointer. If you want, you cannot do this, but you run the risk of modifying x by mistake. Although you will feel not gonna make that mistake, but you should know never underestimate your own sense of making mistakes. Alright, so we have constant double b equal to 0 and a pointer to ax, which will hold the vectors for x. Alright, and we need a double star af, that is an auxiliary array to hold the elements of the PETC object vector f. Alright, then what do we need to do? We need to tell that f0 will be this thing and f1 will be this thing. This is what we need to tell. And x0 and x1 are in the vec x. So we must take these two, give them to ax, so that ax0 will be x0 and ax1 will be x1. This is what we need to do. So first things first, we will read the vector x into the array ax. So vec get array read x ampersand of ax. So why have I used vec get array read instead of simply get vec array? It is a safety interlock to say that ax is only a read-only variable by virtue of being a const double. If it were to be only double, we would have written only vec get array, which we are going to do for f. In fact, vec get array f comma ampersand of af. So these two extract the PETC objects into C objects. This is what it does, and we have discussed this in the previous lectures as well. Alright, so once we have this, we're gonna define AF0 as 1 over B, so 1.0 over B times exponential, so let's say exp real, then B times AX naught minus AX1. Similarly, AF1 is equal to AX0 times AX0 minus AX1 times AX1, not minus, this should be plus. I think I wrote the equation of the circle incorrectly. Well, this is where the mistake was. It's actually plus. This should be a plus. This should be a plus. Alright, so AF1 is this. Now we simply need to restore the C object AF into the PET-C vector F just to complete the entire sequence. So vec restore array read x comma address of AX, and then vec restore array x comma address of AF, and we will return 0 if everything is successful. So this is how we will create the code, and if you feel like you want to modify these things to make your own solver, the code will be available on the website. You can have a go at it. Alright, so at this particular step, we've created the function callback and the residual, so all that we have passed. So once we've set the function, we need to tell SNES that in case I pass some command line arguments, it should set the SNES object accordingly. So set from options SNES, and we will use this. Lastly, we need to solve SNES solve SNES null x. So let me show you the function reference. There appears to be some internet issue. Okay. Alright, so if fx is equal to b, then we need to pass b, but because we have cast our equation in the form fx equal to 0, we pass as a null, and x is the solution vector. So we finally get x as the solution vector. So what do we do once we have a solution vector? Obviously, we're gonna have a look at the solution vector. So we're gonna do vec view x PET-C viewer std out world. Finally, we must destroy all the variables that we've created. So vec destroy x, vec destroy r. We have to pass the addresses, not just the so we have to destroy the memory addresses, not you get the point, the pointers. And SNES destroy ampersand SNES. So all the addresses are passed so that they're destroyed. Alright, so that takes care of this little program. So let me go ahead and create a new target in our makefile. Oops. So we will make a new target. We will call it nlin1. So control H, nlin1. Oops. Passant nlin1. So find next find find next, replace. It's as easy as that, no hassle. Okay, so we have our terminal open, so let us make the target. So make nlin1. Oh, everything's fine. So dot slash nlin1, this will not run. There's a bunch of errors. The reason is we've not told how to make the Jacobian. So if you notice in this entire code we don't have a Jacobian. So minus SNES FD. So it says that it has to create the Jacobian using a finite difference approximation, and it will do that automatically. You don't need to worry about it. And finally, let's have an SNES monitor. Great. So after just 2 iterations, we have convergence. Wait, it doesn't look entirely correct. Well, let us check our function callback. Alright guys, I think there was a small error. This should have been F. Now we are in a position to make, because earlier it was only iterating for 1 iteration, and I thought, okay, that's quite odd. It cannot just converge in 1 iteration. So let me make it again. So now it should work fine. So dot slash nlin1 minus SNES FD minus SNES monitor. Okay, so at the end of 5 iterations we do have convergence to the solution. So what we can do is we can alternately have minus SNES rtol 1e minus 14, the high degree of convergence. So let's run it. So it took one more iteration to converge to 10 to the power minus 16. So once you're near a root, you sort of have a rapid convergence towards the root, but far away from the root, there is no guarantee you will converge quickly towards, in fact, the direction where convergence will happen. Okay, so let me conclude this lecture over here. In this particular lecture, to summarize, we have looked at how we can solve a nonlinear solver using how we can solve a nonlinear equation using the SNES object in PETC. Next lecture, we're going to look at how to pass a Jacobian, and we'll try to do a problem of a nonlinear reaction using PETC. Until then, it's goodbye.